When a current or moving charge is placed in a magnetic field, it feels a force. When a current loop is placed in a magnetic field, it feels a torque, and this causes a net rotation. Actually, this is the basis of every electric generator and electric motor in the world, and it's the concept we'll be exploring in today's problem. Let's take a look. This problem is asking us to find what current is needed through these loops to prevent this ball from rolling down the inclined plane. The reason it wants to roll down the inclined plane without the magnetic field in the first place is because there's a net torque acting upon it. So our first goal will be to find out what is that net torque due to all the forces aside from the magnetic field. And then based on that, we can find out what compensating torque is needed to prevent it from rolling down. So what I'd like you to do on your own first is determine what are the forces acting upon this ball, and then label them on the ball in the actual place where they're acting. For example, if it's in the center of mass, label it there, etc. Take a minute, do that now, and we'll come back and using that find out what the net torque is upon that ball in the absence of the magnetic field. Okay, so here's the forces. We have three forces. The first one is a normal force that acts at the point of contact between the object and the inclined plane, and it points normally to the inclined plane, as its name suggests. Also, we have the weight, which acts at the center of mass, and that points straight down. That's the force provided by gravity. And then the last force is the frictional force, which also works at the point of contact between the ball and the inclined plane, but it points up the plane. Now, out of these three forces, only one of them actually provides a torque. The normal force does not provide a torque because it's parallel to the radial direction, so it doesn't cause any rotation. The weight doesn't provide any torque because it acts at the center of the mass, which won't cause any rotation either. However, the frictional force will cause a torque because the radial direction is not parallel to the force acting. So we do have a torque provided by the frictional force, and to find out its direction, just use the right-hand rule. So the torque provided by that force, you just take the force and curl your fingers on your right hand in the direction of the force, and your thumb will naturally point in the direction of the torque that's being provided. So in this case, the thumb points into the screen as you curl your fingers towards the frictional force. So I'll just write that as the torque provided by friction points into the screen. This arrow, this is just basically looks like the back of an arrow as if it's going into the screen or into your page as you're writing it. Now what we expect is that we don't want this ball to roll, so we expect that the torque provided by the magnetic field should counteract that torque, so it should be pointing out of the screen. Let's just verify that. And so what I'll do is let me just kind of redraw this ball here. And these are the current loops coming across the front of the ball. And if you look at the problem statement, the current is coming kind of out here. I'll draw it coming out like that. And then it goes down the front of the ball, and then it goes back into it. Right now, so just to recall, what is the torque provided by a magnetic field? The torque provided by a magnetic field is equal to the cross product of the magnetic moment with the magnetic field itself. So the magnetic moment, well, we need to find the direction of the torque. So the direction of the magnetic moment is you just take your current loop, and again, use the right-hand rule one more time, and you curl your fingers in the direction of the current in that loop. And then however your thumb points will be the direction of mu. So in this case, we have on this part of the loop, the current's kind of coming out of the screen, and then it curls down along the front of the ball, of the cylinder, and then it curls back into the screen. So as you do that with your right hand, the mu kind of points up in that direction. So what we get is that the dipole moment points up and to the right, and then if we use the right-hand rule one more time to actually find the direction of the torque, we cross mu with B. And so mu is pointing up like this, B is pointing up, and again your thumb, now it's pointing out of the screen or out of your page. So that's the direction of the torque being provided by the magnetic field. And that comes out of the screen, which as we expected counteracts the frictional torque. And so if we set these guys equal, we can get this cylinder to not roll down the inclined plane. And what we're looking for here is the actual current. So what we expect is once we set these guys equal, we can write this in terms of current, and then inverting that equation, we can actually find out what the magnitude of the current is. Let's go ahead and do that now. So I'll set those magnitudes equal. Let's first find an expression for the torque provided by the friction. And this is just acting right on the object itself, so its magnitude is going to be the radial distance crossed with the frictional force. So here the radial distance is from the center of mass to where the force is acting, and then the frictional force is that way. The magnitude of a cross product always equals the magnitudes of the vectors times the sine of the angle between them. And in this case, the sine of the angle is clearly sine of 90 because they're at right angles. So you just have the sine of 90 is 1. So we just have that the frictional torque simply equals the product of the radial distance and the frictional force itself. We don't know the frictional force, so what we need to do is write this in terms of quantities we do know. In particular, we can write that in terms of the mass of the object, the gravitational constant, and the angle of the inclined plane. So go ahead and do that on your own using what you've learned before and get an expression for this without the frictional force, instead in terms of mass, gravity, and theta. Take a minute and do that now, and we'll come back and revisit. To find the frictional force in terms of the other quantities, let's go ahead and draw a free body diagram of this, just moving these vectors around without changing the orientation or magnitudes. So I'll just put them all emanating from the same point. Let's write them here. This is the normal force. We also have the frictional force pointing in this direction. And then the weight vector, which points straight down. And so since the frictional force and normal force are already at right angles, the best way to do this is to decompose the weight vector so that it points along one of those two directions. And so what I'll do is I'll decompose it into a component pointing in this direction, and then a component pointing in, let's make it this direction. So these are at right angles, and you can just convince yourself using a little bit of geometry that this angle is theta, the same angle as that. And then using some trigonometry, we'll find that this component is w cosine theta, and this component is w sine theta. And so the frictional force must equal, these vectors must be equal and opposite. The frictional force must equal w sine theta to keep this thing in equilibrium. And so I can rewrite this frictional force as r times w sine theta. The weight is just mg, so it's just r times mg sine theta. And so this is the expression we have for the magnitude of the torque provided by the frictional force. The next thing we need to do is find the magnitude of the torque provided by the magnetic field, which is this quantity. And I'd like you to go ahead and do this on your own. It's going to take a couple of steps because you not only have to determine the angle between these two vectors to write it kind of in this form, you also have to determine what the magnetic dipole moment is based on the current and the area of the current loop. Go ahead and take a minute and do that now. We'll revisit in a moment. All right, now rewriting the cross product, it's going to equal the product of the magnitudes of the vectors times the angle between them. And since that angle is not clear that it's the same angle as that, it's the angle between the mu vector and the b vector. It's not clear that it's the same angle, so I'm just going to rewrite it with a different notation as sine of theta of mu b. Now we have these various factors here, so let's look at them one by one. The dipole moment has a magnitude that equals its current times the area of the loop itself. So in this case, we have a cylinder, and the loop is kind of wound around the long part of the cylinder. So it's basically the current loop is just a rectangle, and one side of it is the length of the cylinder, which they call L in the problem, and then the short side is 2 times the radius, or the diameter of the cylinder. So the area of it is just going to be the length times the width, which is L times 2R. So mu is going to be the current times the area, which let me just go ahead and write that one more time. So current times area times B sine theta mu B, and then the area, as I noted, was 2R times L, because it's a rectangle, length times width. The current going through the cylinder, through the loop rather, it's actually 10 times the current through each one of the wires, because it's wound 10 times around. That's stated in the problem as well. So it's going to be 10 times I, where I is a current through the wire, it's through a single wire. And then we have B for the magnetic field. Finally, we want to find an expression for theta mu B in terms of some other constants in the problem. So let's determine how that theta is related to this theta. And what I'll do is just kind of redraw the picture here. So let me just draw this winding I'll draw that right there. So this is that winding, the windings. And if you take a look at this picture, this should actually be parallel to that inclined plane. So that means that this angle is equal to that angle. So this is equal to theta. And what we're looking for is the angle between mu and B, because that's the angle that's going to be relevant in the cross product. And that's that angle right there. So let's just use a little bit of geometry. We can kind of move this angle up here. So this angle is also theta because they're corresponding angles. And then if you look at this picture right here, this is 90 degrees. So this small angle right here is 90 minus theta, and this is also 90 degrees. So if this is 90 minus theta, this has to be theta. So this theta mu b is actually equal to theta also. So I can rewrite this as sine of theta. Right? And so that is the magnitude of the torque provided by the magnetic field. Setting this equal to the magnitude of the torque provided by the frictional force, we'll find that the sine thetas cancel, and then the r's cancel, and that makes sense because r wasn't given in the problem. And actually theta was given in the problem, but it's not needed. And so when we solve, we can just isolate I on one side of the equation to find the current through the wire, and solving using the numbers given will give you 2.45 amps. So that's the current traveling through the loop that's necessary to keep this cylinder from rolling down the inclined plane. All right, so that's the answer. Let's take a look at how we got that by summarizing. In this problem, we were asked to find the current necessary to prevent a cylinder from rolling down an inclined plane. First, we determine the directions of the magnetic and frictional torques to balance the cylinder. Then we determine the actual frictional torque using a free body diagram. Next, we determine the magnetic torque using the area of the current loop and the currents. Finally, setting these equal, we solve for the current. So that's it for this problem. I hope it was a pretty useful example on how to solve for torques on current loops and magnetic fields. If you have any comments or questions, please leave them on the link attached to the video, and we'll see you next time.